In this video, I'll show you how to analyze the experiment. It's a Vernier experiment, but it's available in many sources. How to determine the rate order in the decoloration of crystal violet. And we're doing this in parts 1 and 2. Part 1 studies the concentration via absorbance of the purple crystal violet plus reactant as it decolors. Part 2 uses the same reaction but runs it under 3 or 4 different hydroxide concentrations so that you can determine the rate order in hydroxide. So part 1 is what we'll do first. Now, I've got to switch over to an application. We're going to use the Logger Pro application, which you can download from the Vernier Corporation website with their permission, of course, and so you have to contact them for that. Now here you see I have brought up the Logger Pro application, and you see a place for data sets. You can type in there and get any graph that you would like using this, or you can bring the data in from one of their probes. However, what we're going to do, we've used the Graphical Analysis program to record data from the remote Vernier sensors, the so-called Go Direct sensors, and they have a colorimeter which we have used, and we have stored the file that was produced. It has a .gmbl extension on it. Let's show you that I have pulled up one of these from the disk. And when I pull up the Logger Pro program, the challenge now is to bring that file in. It's not terribly easy. I want to show you how to do that. So what we've got here is, I'll just click on Open, and we bring up this here. This is the disk that comes with Logger Pro, so none of these directories are going to be useful to us. So we're going to go to this PC and Documents and our AP Chemistry folder. And here I have stored that under Laboratories and Kinetics. Now, you don't see any files here. I don't know why that is, but that's what happens. You have got to physically type in the name of the file that you're looking for. And it's copy of CV and, so we're going to type that in. And you'll see 4 files come up. We're going to choose the 0.05 molar sodium hydroxide. You're also going to do this and this. So there's also should be a 0.1 molar sodium hydroxide. We'll use the 0.05. And when we open it, we don't see the file pop up here, and we'll get an error code. It says that the file was created with a different application, the Graphical Analysis application. So it says the file will open, but some features may not be supported. It'll support all the features that we need. So if we bring it in, now we see the disappearance of the grid where we could type in numbers. The numbers are in memory here, but all you see is the graph. So what I'm going to do here is show you that this does in fact look very much like a logarithmic decay curve or exponential decay curve. And what we need to do is determine, is this in fact an exponential function? Now, how we're going to do that, we're going to do it fairly rigorously. We are going to Click on Data, and we are going to create a new calculated column. We're going to call it Natural Log of the Absorbance. And we'll give it a short name, LN ABS. Now, it says data set 1. We don't see any other data set. Well, there's a data set 2. And we're going to type in the expression. We start off by clicking on Function because we want the natural log function, which is right here. And then in the parentheses, the argument we're going to use, the variable, is of course absorbance. We would like the natural log of absorbance versus time. So we now click on Done, and you don't see anything because there is in fact a new data set created that is the natural log of each of these absorbances as time goes on. Now, we're not going to take a look at those numbers. It doesn't make sense to add the extra step. So what I'm going to do is I'm going to click on Insert, and I'm going to click on Graph. And as you can see, here is the natural log absorbance on the coordinate, and time in seconds on the abscissa. And that looks a great deal like a straight line. Now, what we're going to do, I want to get rid of this point, because this point came up like while the colorimeter lid was being closed. So we're going to paint out just that part of the graph that looks straight, and we are going to do an analysis of that, and we're going to get a linear fit. And we have created a linear fit. And that straight line does not deviate from these points, these colored points, at all. Moreover, it gives us the information we want. The natural log is equal to mx plus b. We've seen that that's a linear relationship. So here is the slope, which is the rate of the reaction, and the b, of course, is the intercept. Here's the intercept at minus 0.7849. The correlation is -1. That's a perfect correlation. So this slope is very reliable for this particular run. Okay, that's the first thing I wanted to show you, and that's what you need for part 1, because you want to show a graph of the natural log of the absorbance versus time to show it as a straight line, and that straight line tells you that it is a first order reaction in the crystal violet. Okay, we're going to get rid of this. Well, I guess we could easily throw it in the back, but let's just get rid of it. Now, each one of these lines for the 4 different concentrations of hydroxide is somewhat different. And we noted in the lab that, in fact, as you decreased the concentration of hydroxide, the starting point on the absorbance crept higher and higher, because in the time it takes for you to first mix the samples and then put them in the cuvette holder, close the lid, and start recording data, a certain amount of the crystal violet has been decolored. And that's going to differ depending on the concentration of hydroxide you're using. So what we'd like to do is find a point on each one of these curves, the 4 curves, that is exactly the same time from mixing. Now you can do that from your data because you have kept track of how long it took you to start collecting data from the time of the mixing. So what are we going to do? Well, let's look at Analyze again, and let's look at Examine. Well, as you can see, if you move along here, you can see what the time is and what the absorbance is. That's not what we're looking for. We're looking for a slope. So you can determine how many seconds you need to go along this curve before you need to get the rate. For each one of them, it should have the same lag between mixing and this recorded slope for all 4 of the runs. And then you can compare those. We'll talk about that in a second. Well, what do? Oh, go up to Analyze again. Let's take away Examine and put Tangent. Okay. Now, you may not be able to see that black tangent line, but it creates the tangent, and you can find it. See, the number of seconds shows up in the box, and the slope. So, say you had 40 seconds, so let's see, well, 39. 39 seconds, absorbance slope is minus 0.000141. Now you're going to change that to a positive number, and you are going to say 1.41 times 10 to the negative 3. Right. You're going to do this for each one of them at the same elapsed time from mixing, and each one of those is going to create a slope. You're going to put that in your lab notebook, indicate what the elapsed time was when you did that, and you're going to have 4 different slopes, positive numbers. Okay, now it's time for you to get out your favorite graphing program. Well, LaRPro will do the job, but if you like Excel, try that. And I suggest you mock it up in your lab notebook first. That way you are going to know what it looks like. So, on your vertical axis, you're going to plot the rate. And there it is. 1.26 times 10 to the negative 3. That's for 60 seconds. Or whatever the time is, you find the rate. And then you go and do the same thing for your other 3 graphs. Each one of them will have a different slope. And for each one of those, you probably save the concentration of hydroxide right in the title of the file. Now, you're then going to get an XY axis. Let's just do that so you'll see what to do. And you can type in the molarity here for X, and molarity of hydroxide here. They'll go down here. And the Y would be the slope, which you would call the rate. And you're going to have 1, 2, 3, 4. And you will get a graph here. And that's the second thing you need to report for your laboratory report. And of course, your conclusion is going to say what order the reaction is in crystal violet. You get that from part 1. And you might want to report what the rate was, what the slope was. And then also the second graph gives you part 2. And if you get a straight line, it's first order. If you get a curved line, it's second order in part 2 for hydroxide. That should take you all the way through your lab report.